Welcome to the video lecture series on digital image processing. In our last class, we have started our discussion. We have covered the fundamentals of color image processing. We have seen what is a primary color and what is secondary color. We have seen the characteristics of different colors. We have seen the chromaticity diagram and the use of the chromaticity diagram. And we had started our discussion on color models, and there we just started the discussion on RGB color model. Today, we will start our discussion with the color models. So, we will complete our discussion on RGB color model. We will also talk about the HSI or hue, saturation and intensity color model. We will see how we can convert the colors from one color model to another color model, that is, given a color in the RGB space, how we can convert this to a color in the HSI space, and similarly given a color in the HSI space, how we can convert that to the RGB space. Then we will start our discussion on color image processing techniques. So, we will talk about pseudo color image processing, and there mainly we will talk about two techniques. One is called intensity slicing and the other one is gray level to color image transformation. So, let us just briefly recapitulate what we have done in the last class. In the last class, we have mentioned that all the colors of the visible light or the visible spectrum, color spectrum, occupies a very narrow spectrum in the total electromagnetic band of frequencies or band of spectrum. And the visible spectrum, the wavelength normally varies from 400 nanometer to 700 nanometer. So, at one end we have the violet and in the other end we have the red color. And out of this, we normally take three color components, that is red, green and blue as the primary color components, because we have mentioned that in our eye there are three types of cells, cone cells, which are responsible for color sensation. There are some cone cells which are responsible, which sense the light in the red wavelength. There are some cone cells which sense the green light, and there are some cone cells which sense the blue lights. And these lights are mixed together in different proportions in an appropriate way, so that we can have the sensation of different colors. And this is the main reason why we say that red, green and blue, they are the primary colors, and by mixing these three primary colors in different proportion, we can generate almost all the colors in the visible spectrum. Then we have talked about two different colors, two types of colors. One is the color of light, other one is the color of the pigment. Now, color of the light, as we see any particular object, we can see the color which is reflected from the object because of the wavelength of the light which gets reflected from the object surface. Now, when it comes to pigment color and a color falls on it, then the pigment color, it absorbs a particular wavelength out of the three primary colors and reflects the other wavelengths. So, the primary colors of light are really the secondary colors of pigment, and the secondary colors of light, they are the primary colors of pigment. And because of this, the colors of light, they are called additive primaries, whereas the colors of the pigments, they are called subtractive primaries. And here you can see in this particular slide that the three primaries of light, red, green and blue, when they are mixed together, then red and green mixed together form what is called form the yellow light. Then green and blue, when they are mixed together, these two form the cyan, and red and blue mixed together form the magenta. And red, green and blue, all these three colors together form what is the white light. Similarly, when it comes to pigment primaries, yellow, which is a secondary color for light, is a primary color of a pigment. Similarly, magenta, which is a secondary color of light, is also a primary color of pigment. Cyan, which is a secondary color of light, is a primary color of pigment. And here you find that when these pigment primaries, they are mixed together, then they form what are the primary colors of light. So, yellow and magenta, these two together form the red light, yellow and cyan mixed together form the green light, and magenta and cyan joined together, mixed together, form the blue light. However, all these three pigment primaries, that is yellow, magenta and cyan, mixed together form the black light. So, this is the black color. So, by mixing different colors of light or the different colors of primary colors of light or different primaries of the pigment, we can generate all types of different colors in the visible spectrum. Then we have also seen what is a chromaticity diagram, and we have seen the usefulness of the chromaticity diagram. So, the chromaticity diagram is useful mainly to identify that in which proportion different primary colors are to be mixed together to generate any color. So, if I take 3 points in this chromaticity diagram, say one corresponding to green, one for the primary red and other for the primary blue, then given any point within this chromaticity diagram, I can find out that in which proportion red, green and blue they are to be mixed. So, here you find the horizontal axis tells the red component, the vertical axis gives us the green component and the blue component. So, if I write this as x and this as y, then the green component z is given by 1 minus x plus x plus y. So, I can find out that how much of red, how much of green and how much of blue, these three components are to be mixed to generate a color which is at this particular location in this chromaticity diagram. It also tells us that what are all different possible shades of any of the pure color which are available in the light spectrum that can be generated by mixing different amount of white light to it. So, you find that we have a point of equal energy that we have mentioned in the last class in this chromaticity diagram, which is white as per CIE standard. So, if I take any pure color on the boundary of this chromaticity diagram and join this with this white point, then all the color points, all the colors along this line, they tell us that if I mix different amount of white light to this pure color, then what are the different shades of this color that can be generated. Then we have started our discussion on the color model, and we have said that color model is very, very useful to specify any particular color. And we have said we started our discussion on RGB color model, and we have discussed in our last class that RGB color model is basically represented by a Cartesian coordinate system, where the three primary colors of light, that is red, green and blue, they are represented along three Cartesian coordinate axes. So, we have, as per this diagram, we have this red axis, we have the green axis and we have the blue axis. And in this Cartesian coordinate system, the color space is represented by a unit cube. So, when I say it is unit, that means the colors are represented in a normalized form. So, in this unit cube, you find that at the center of the cube we have R, G and B, all these three components are equal to 0. So, this point represents black. Similarly, the furthest vertex from this black point or the origin where the red component is equal to 1, green component is equal to 1 and blue component is equal to 1. That means, all these three primary colors are mixed in equal proportion and this point represents white. The red color is placed at location 1 0 0 where the red component is equal to 1, green component is equal to 0 and blue component is also equal to 0. Green is located at location 0 1 0 where both red and blue components are equal to 0 and the green component is equal to 1, and blue is located at the vertex location 0 0 1 where both red and green components are equal to 0 and blue component is equal to 1. So, these are the locations red, green and blue, that is 1 0 0, 0 1 0 and 0 0 1. These are the locations of three primary colors of light, that is red, green and blue. And you find that in this cube we have also placed the secondary colors of light, which are basically the primary colors of pigment, that is cyan, magenta and yellow. So, these three colors cyan, magenta and yellow, they are placed in other three corners, other three vertices of this unit cube. Now, find that from this diagram, if I join these two points, that is black at location 0 0 0 with white at location 1 1 1, then the line joining these 2 points black and white, this represents what is called a grayscale. So, all the points on this particular line will have different gray shades, they will not exhibit any color component. Now, given any specific color having some proportions of red, green and blue, that color will be represented by a single point in this unit cube in a normalized form. Or we can also say that that color will be represented by a vector, where vector is drawn from the origin to the point representing that particular color having a specific proportion of red, green and blue. So, this is what is the RGB color model, and you find that from this RGB color model we can also have the cyan, magenta and yellow components by simple transformation. So, given any point in the RGB color plane, what we can do is, if I look at the different color shades on different faces of this color cube, you find that the shades will appear like this. So, in this color cube, you find that we have said that the point 1 0 0 that represents red, and you find that along the horizontal axis the color varies from red to yellow. Similarly, this is a point which is 0 0 which is 1 1 1. So, this point represents white color, and in this particular case all these color components, that is red, green and blue, each of these color components are represented by 8 bit. That means, we have altogether 24 different color shades which can be generated in this particular color model. So, the total number of colors that can be generated is 2 to the power 24, and you can easily imagine that is huge number of colors which can be generated if we assign 8 bits to each of the color components, that is red, green and blue. But in most of the cases, what is useful is called safe RGB model. The safe RGB model, in safe RGB model we do not consider all possible colors, that is all the 2 to the power 24 different colors, but rather the number of different colors which are used in such cases is 216. So, these 216 colors can be generated by having 6 different colors in red, 6 different color shades in green and 6 different color shades in blue. So, we find that on the right hand side we have drawn a safe RGB color cube. So, here we find that we have 6 different shades of any of the colors, that is red, green and blue, and using these 6 different shades we can generate up to 2 to the power 16 different colors, and these 216 different colors, and these 216 different colors are known as safe RGB colors because they can be displayed in any type of color monitor. So, you should remember that in case of true RGB, though we can have total of 2 to the power 24 different colors, but all the color displays may not have the provision of displaying all the 2 to the power 24 colors, but we can display 216 colors in almost all the color displays. So, this is what is called safe RGB color model, and the corresponding cube is the safe RGB color cube. So, it is quite obvious from this discussion that any color image will have 3 different color components, one color component for red, one color component for green and one color component for blue. So, if I take this particular color image, you find that the top left image is a color image and the other 3 are the 3 planes of it. So, the red color component of this color image is represented in red, the green color component is represented in green and the blue color component is represented in blue. So, here we find that though we have represented these 3 different components in different colors, that is red, green and blue, but they are actually monochrome images, and these monochrome images or black and white images, and these black and white images are used to excite the corresponding phosphor dot on the color screen. So, the red component will activate the red dot, the green component will activate the green dots and the blue component will activate the blue dots. And when these 3 dots are activated together with different intensities, that gives you different color sensation. So, obviously for any type of color image like this, we will have 3 different planes, one plane corresponding to the red component, the other plane corresponding to the green component and a plane corresponding to the blue component. Now, as we said that this red, green and blue, they are mostly useful for the display purpose, but when it comes to color printing, the model which is used is the CMY model or cyan, magenta and yellow model. So, for the color image printing purpose, we have to talk about the CMY model. However, the CMY can be very easily generated from the RGB model. So, as it is obvious from the color cube, the RGB cube that we have drawn, and the way the CYM, cyan, magenta and yellow colors are placed at different vertices on that RGB cube. So, from there it is quite obvious that specified any color in the RGB model, we can very easily convert that to CMY model. The conversion is simply like this, that given RGB components, so we have the red, green and blue components of a particular color, and what we want to do is we want to convert this into CMY space, and the conversion from RGB to CMY is very simple. What we have to do is we have to simply make this conversion, that CMY is equal to 1 1 1 minus RGB. So, here you remember that these RGB components are represented in the normalized form, and similarly by this expression the CMY components that we get, that will also be represented in normalized form. And as we have said earlier, that equal amounts of cyan, magenta and yellow should give us what is a black color. So, if we mix cyan, magenta and yellow, these three pigment primaries in equal proportion, then we should get the black color. But in practice what we get is not a pure black, but this generates a muddy black. So, to take care of this problem, along with C, M and Y, cyan, magenta and yellow, another component is also specified, which is the black component. And when we also specify the black component, in that case we get another color model, which is the CMYK model. So, the cyan, magenta and blue, so this is CMYK model. So, cyan, magenta and yellow, they are same as in CMY model, but we are specifying an additional color which is black, giving us the CMYK model. So, you find that in case of CMYK model, we actually have 4 different components: cyan, magenta, yellow and black. However, given the RGB, we can very easily convert that to CMY. Similarly, the reverse is also true. Given a specification, a color in the CMY space, we can very easily convert that to a color in the RGB space. Thank you.